myself. Okay. So my PhD is in data science, and I'm using remote sensing and other methods to monitor rewilding conservation and nature-based solutions. And I'm working not just with remote sensing now, but also, for example, with camera traps to object detection and stuff like that. And I've done a lot in terms of remote sensing. I've done a lot of stuff. I've worked with UAV data. I've worked with citizen science data. I've worked with camera traps now, remote sensing. So I have some years of experience because I didn't do my PhD directly after my master's. And now I'm much more becoming about machine learning and data engineering, so the boring office work. My focus on my PhD is basically on retrieving traits and then relating that to some pressures, that in my case, nature-based. So basically, for example, herbivore pressure and conservation that uses nature solutions. Okay, that's the boring part. So my first question for you now is, wait, you didn't, then everybody can try to answer that one. What is machine learning or artificial intelligence?
Machine learning is inside of artificial intelligence.
Okay, that's a good question, but it doesn't define right? What is inside the bottle. It doesn't define the water. So I will try to kind of give a small answer about this, but machine learning basically is about teaching your computer to do some task. That's it.
It's a black box too.
It's not black box for people, for me. No, it's my black box. But an artificial intelligence is you try to simulate intelligent behavior. So of course, machine learning is part of artificial intelligence, and a lot of artificial intelligence is machine learning now. So my question now is, okay, this is a bit weird. Okay, is this machine learning? Does it move? Oh, it doesn't move. Oh. It is supposed to move. Okay, it's moving. Okay, so I think I have to click the button. That's the issue. Okay, so is this machine learning? So this is a very famous screensaver for Windows some time ago, in the 90s.
No.
Okay, no, it's not machine learning because he set a set of rules, and the computer just behaves accordingly. And this behavior that looks intelligent, it's kind of like when systems design, sometimes it outputs something that makes sense, right? It's a bit like what's happening here. So you set up those 3 types of rules, and then you have this flock behavior, which then this became a field of research by its own. And if I move to the next slide, is this machine learning? This is machine learning. So what's happening here is you set up very basic rules for the agents, and then there's a machine learning algorithm behind that is teaching the agents to hide from each other, and they play hide and seek. And this is a very funny video. I really advise to check these videos, this YouTube content, 2-minute papers, because they have really cool stuff. And this video is really cool because the computer actually learned how to cheat, like to break the rules of the game so that they win. It's very cool. And this is adversarial learning. Okay, so it's very nice actually presentations in this class. So basically machine learning is what I'm saying. You are about making your computer to do something, right? And the big difference between machine learning and normal programming, which was the first case, is you program the rules and you put the data in and you get the result. And in the case of machine learning, you put some result in, some data in, and then the program comes out. But you sometimes don't know what the program is about. So people say it's a black box. And of course, the problem is there's a lot of problems with big data and biased data, right? And there's been discussions now about climate impacts of the big computers. And this is all a problem of machine learning. Because recently there's been a theory of scaling your computation will solve your problems. Basically just increasing the number of neurons on the neural network until it solves the problem. Okay, going more basic, how does machine learning actually work? So let's say that you skipped algebra or you skipped high school, kind of, and the professor gives you a bunch of points and says you make a line, find the equation of the line that fits this point the best, right? And all you know is that y equal mx times x plus c, being x, the x's and y, the top, right? So the way you could go about it, you could just draw a line and then say, compare the values of that line against the values of the scattered plot and say, okay, this is a good model or a bad model, right? But you look at the data and you are smart enough to say that this line is a bad line. And this line would be a better line, right? And then you edit, and then it's a bit better, and you'll try again. It's a nice choice, right? So what you are doing here is visually, now you are not comparing the values, right? You are visually comparing the difference between your model and some data that you have on input. And every time you are choosing the model that is closer to the best result, right? So, so this is exactly how computers do. Okay, they just try over and over until they find a model that fits. So this would be a machine learning approach to solve a linear model. Okay, you pick up your model and then you try different lines until you find a line that more or less fits all the points equally well. Okay, and then this becomes something that is called optimization problem, which is basically trying to find the best solution for a combination of parameters. In this case, for example, our parameters will be M and C, and you'll be trying to change M and C until your error is low. Okay, so this is machine learning. This is what happens in all algorithms of machine learning, from the probabilistic ones to the non-probabilistic ones like neural networks. Okay, so basically they just change the parameters until the model is supposed to be similar. So at its core, basically machine learning is just a function that transforms X to Y, or an input set of variables to an output variable or multiple output variables. And then you have some representation of the algorithm. In our case before would be the linear model, right? And then you have a way to evaluate your model. That would be an error equation, error metric. And then you have some optimization algorithm that finds the best solution. In general, also all these optimization algorithms, they compute, what they do is they compute nearby changes in the different parameters, and they see how the model improves or not. Okay, so that's also, all of them work this way, but then they have like multiple computations at the same time, less computations using Bayesian inference. It varies. Okay, so these are the three main components, and this goes from neural networks to adversarial networks. They all kind of have this, and then they have more, of course, in some cases. So is there any questions about this machine learning? Was it clear? I decided to do the introduction because I don't know how the background really is.
Maybe the philosophical question, but this, at the end, these machine learning, they use simple rules, right, to optimize. So is it actually artificial intelligence? Is machine learning part of artificial intelligence or not really?
I would say that artificial intelligence can use machine learning. So machine learning is a way of, okay, you have a complex situation and you cannot come up with a model that actually explains like F equal MA, but you could throw a bunch of projectiles and collect the data and put it in a model and then do something else with the data. So machine learning is not necessarily artificial intelligence, it can be, but in general, machine learning is a tool for making computers learn how to map a function. Okay.
I would have thought, like, for example, the optimization of linear regression is not machine learning.
Yes, but I'm not saying, I'm saying this is a way of machine learning to solve this problem. Okay, and I was trying to give an example. There's this dragon, it's not machine learning because it will be stupid to solve this way, this problem this way. It's basically an algebra operation to get a linear model from there. Okay, but I decided to use machine learning to like, oh, you can try it. Okay, it's an optimization example.
Fitting of the best to best curve, that will be
the way, let's say,
the models.
What was there was not necessarily, no, not real machine learning. It was an optimization solution to the linear model. But so let's not confuse. But that's the example just to keep it very simple that you can understand. Because if I show you a random forest and say divide the different parts, everybody says yes, yes, but then they don't really understand what is happening in terms of the model. This way they can see, okay, and basically what happens with the models is exactly that, but with more complex algorithms. Okay. Okay, but let's give some examples then of machine learning algorithms. The ones you were talking, for example, if I show you this and say, oh, the algorithm picks up all the data and picks up, finds the groups that are pure or similar between them, and then makes a rule and separates. Okay, so where is the minimization in a random forest? maximizes the group purity. Okay, comes up with rules, tests different combinations of rules and features in each node, and says this group is more pure, it goes that way, and that group is not pure, it goes that way. Okay, and then in the end, you would have an object that is basically just sets of rules. The first data comes in, or is it bigger than 10, lower than 10, it goes this way. Okay, so this is, now you understand that it has three parts: representation, minimization, and then you have somewhere when it's training, it has an optimization part. Okay. So that's the random forest. And then you usually have a set of parameters like number of trees that you are going to use, how deep you are going to go, how many points per class, it varies. Support vector machines, what do? They have imaginary sets of points. They try to find the hyperplane, let's say this way, but it can be, if you have only two sets of variables, it's going to be a line. So they try to find the best separation between groups of data. And besides that, they also transform your data. For example, if this will be your input data, they multiply it by x squared so that it becomes like this. And then you can define an hyperplane in this dimension and transpose it to this place. And it's called support vector machines because the planes are defined in a vector format. So they are support vectors of the plane. Okay, this makes sense. And what it's doing is maximizing the separability. So that's the optimization problem in support vector machines. Neural networks, which are the famous ones, are basically just each neuron is like a linear model pushed into an activation function. So that's a function that transforms into a non-linear behavior. And then what it tries to do is change the parameters of the linear model. So that in our case before it was the M and the C. So it usually calls the weight and the bias, changes those parameters until your neural network is able to predict the output. So this is how neural networks work. And then you can, the cool thing with neural networks is that you can just transport neurons everywhere. And you can separate them between them, and you can have different activations each neuron. You can do everything almost with neural networks, okay? And for example, this is the part of the scaling. So the GPT-3, the famous neural algorithm, has 175 billion parameters. So
what's the difference between neural network and deep learning in your
I think the depth, the amount of neurons and layers, I don't know where the limit is directly, but this one is definitely deep. Yeah, but there's no standard difference, and there's a lot more stuff because you can also have transformation layers, so layers that actually transform the input data to something else. That's usually convolutional stuff. So neural networks, the advantage is they are very plastic, and they store matrix. Right? When you finish your training, you have a matrix of weights and biases, and it's very easy to transport that information to another place. Let's say, of course, 175 billion parameters might be a lot of megabytes, but in general, a neural network with thousands of parameters, you can, it's like a few kilobytes because it's just a matrix of information. Okay, so the question is always how we find, so because all these different parameters, how do we find the best combination of these parameters, right? And this is always one of the main issues in machine learning, right? And often you see people just apply the algorithm out of the box, and that doesn't mean necessarily it's the best version of that algorithm. And this is where you can think of how can we automate this system so that you don't have an expert every time looking at the data and then deciding this is our number for us to do that, right? That's one of the main issues with machine learning. Then also in machine learning, you have all this data preprocessing. So when your data comes in, you think, do I need to rescale my data to have a much broader variation in my data set? Do I need to resample my data so that I deal with unbalance of my classes for my task, right? So these are also other problems of machine learning. You have to solve not just the algorithm, but also what do you do with the data when it arrives, right? And usually this is in the data engineering part. So if you work as a remote sensing guy, you got some satellite data, you see some missing data, and then maybe you do some interpolation to find the missing data. This is all the stuff that you are doing. Can this be automated? Can this be automatically, right? So all decisions that you are making based on expertise. And then you have the other part that, for example, you do in the RTM. You can do all this transformation for PCAs, SVDs, trying to find which combinations of features. If you have hyperspectral data, do you need to select specific bands? So all those steps are expert-based, right? It requires that you sit in the computer, you program it, you decide it, right? Based on maybe some other research. And if you actually go, for example, for sklearn, there's some hundreds or dozens of algorithms that you can apply in all of these steps. It's an absolute nightmare to know what you need to do. So this is the main issue when you apply machine learning, right? Is what algorithm?
What does happen in feature decomposition?
No. You try to find the best features. So you have 10 features, and some of them are autocorrelated between them, and some of them represent the same relationship with the data, right? So for example, height is related with the rain, but so is temperature. They are kind of both correlated, right? So maybe instead of in your model using both in separate, you can use them together. You understand? You combine, you make a new feature that is kind of the combination of those two features. So it's kind of, you try to reduce the number of dimensions of your data, okay? Or make something that is orthogonal, because then there's mathematics into it. So you don't have orthogonal features, you might cause autocorrelation to impact your models. Although most of these machine learning models have inbuilt autocorrelation ways to solve it. Okay, so this is more questions. So this is the issue, right? What the best parameters of the model, what's the best algorithm, what steps do I need to do, where can expertise comes in, right? The remote sensing guy will use NDVI for vegetation, another guy from soil will use another index, right? Because it's the part of expertise. And if you want to apply this some kind of in a business way, if you want to make this automated, for example, in your cloud service to a client, you cannot have an expert look into everybody's case if you're getting hundreds of requests, right? So you need to have maybe some kind of automatic way of doing this, right? And one of the strategies to solve machine learning is, again, putting your algorithm into an optimization step, right? So I, again, have a metric that will compare my output against my input data, right? And I'm trying to find the best way to minimize this error. And there are some strategies, right? You can go about it in a systematic way. For example, you could say, I'm going to try with 50 trees in the random forest, 100 trees in the random forest, 250 trees in the random forest. Then I'm going to try with other parameters to make this matrix of parameters. And then you see whichever gets the best result is the best model, right? You can just decide, I'm going to do a random set of parameters, or you can try to use probabilistic approaches. So these are kind of the three main ways to go about it. And then there are, of course, within optimization, some dozens of algorithms that you can use. The issue runs into computation time. You have to compute a lot of stuff to make this work, right? So we will do.
Speak more on Bayesian optimization.
So the Bayesian optimization, what it does is it looks at your current status. So for example, you start your model and you run, for example, 10 different combinations. And he says, okay, based on the error that I'm seeing, I'm going to try this, changing this parameter. Okay, so he uses the current evidence to set up the next evidence. So it's very close to the discussion process approaches. Okay, it becomes as a prior expectation, and then it looks to where changing a parameter might likely be improving my model. So the problem with this approach is that it can always find improvements, and usually, for example, in a grid search, so if you try systematically, it will eventually be over. But in a Bayesian optimization, you could run it forever, because it will always find something to tweak. And of course, at some point, it will be overfitting. So the Bayesian optimization, you kind of have to find a balance between how many trials am I going to do and how much time I have left.
Does it change the properties of your inputs?
In what sense?
In parameters, like when you selection of the final parameter?
Depends on what you're doing. If you're doing a Bayesian optimization just of the model parameters, then it changes nothing on the data. But in some cases here, where you are using auto machine learning and feature preprocessing, you could make the feature preprocessing be part of your optimization. Then it would change the feature preprocessing as well. Okay. So let's go to Google Colab. Now, you can either follow me, or you can, follow me, or you can just write it in your own part. But be careful with internet; it's not very strong. So I sent you a GitHub link, right? So it is my web page here, and you will have to download this data set. But you have to click on it. So if you have GitHub, you can just clone, and you know how to use it. Sorry. It was in the WhatsApp. Sorry. So you download it here, and it should download your 5 megabyte file. Okay. And I have to take it to my since Slack. It doesn't matter, I can do it here. So basically you just downloaded it and now you have to unzip it. Okay, just extract here. It says so many questions. Right? And now you have 2 sets of data, and this is the idea here is I want you to have the same folders as I have in Google Drive. Okay, and this is the best way I found to do it. So in this folder you have nothing. You're supposed to, by the end of the tutorial should have the models here. You should have the output predictions here in the tables and in the images. And then you have a shape file that kind of goes to the place that we are doing our research, our small example. And here you have satellite data downloaded from Google Earth Engine, which you are not going to run because it takes some time, but if you run it, you'll get something like this in your computer, okay? And you'll also get, it takes a bit of time always, you'll also get this information about the angles, which are basically per image, you have kind of how much is the azimuth. We need this for the cross sale, right? And I averaged everything, so make it simple. So once you have this, basically what you have to do is you have to go to your Google Drive. It's in German. Just starten, I guess. What? Why is it in German in my computer? Yeah? Oh, maybe I turned off my Google Drive. That's fine. I turned off my Google Drive. That's why. Oh, I don't know my password. So, but let's. How do I translate this? Okay. Is this one? Oh, let's start, and that's the place I need to. Where do I do the login? Oh my God, here? Here? Ah, okay, yeah. You're right, you're right. I think I was in the company version, right? Oh, thanks. Sorry. I think I turned off my Google Drive in the computer, so it's disconnected, the normal procedure. So this is where I was working, but I'll make my new other Google Drive, and I'm going to just build the set here. And what I need to have is I need to set my root data set. So if you don't do the same way, the problem is that the paths to the files will change. So the naming will change. So try to have it exactly as I do. So here you create a new folder called Senseco, like this. And you can go to it. And you just go here and pick up whatever is inside here. And just drag there. Okay. It should do it. Should be very fast. And here in this one, you just put the Senseco data. Try not to put it inside a folder. Okay. So by the end, you should have this a Senseco, and a Senseco has 2 data. And then here you have the satellite images, and here you're going to have your outputs and some of the pointers, the spatial pointers. Okay. Cool. The people who are doing it, they managed. Folders in Senseco, they will be, so in the shape files is basically just to crop the satellite image. In the GitHub. In the GitHub, here. So here, all right, here you have this section, and you have to. If you don't have Git, you can just. If you have Git, you just clone. If you don't have, you have to like this. Okay. It's very. It looks complicated. This is the most complicated part. Okay. I know that this is the most complicated part. You have to go click on the button to open, and then you have to download there to do these 2 steps. Because otherwise it doesn't work. It downloads the web page. Okay. Pronto. And I'll show. Then to run your Colab notebooks, basically just go here, and they are by order. So for example, we can do the first machine learning model. Just press on it. Should open a window here. The internet might play a trick. And then you just press open in Colab, and it will open a Colab notebook. Okay. One warning is this: everything is online, so every other day they update the packages. So sometimes there are errors. Cross your fingers that there will be no error. Okay. Yes. So you go back. So once you are here, so you go to my folder, Colab Notebooks. You press on the Colab Notebook, and it opens over here. Okay. And if you want to run it in your own Colab, you have this button, and you press it, and it should open Colab Notebook. Okay, so this is a good way to share to your friends as well.
The folder in the inside is not Senseco or Senseco is through data.
What?
The folder.
No, it's nothing to do with that part. This is in the GitHub.
This is it? Okay.
This is in the GitHub page. Okay. Is everybody was trying to do this here, or did you guys manage from Spain? You guys managed?
On the way.
On the way? Okay. But I'll move forward then, because huh? It's not working. Okay, so, but let's move forward, otherwise we don't get to the RTM inversion. Okay, let's move forward, otherwise the RTM inversion doesn't happen. It's recording, okay? So it's relatively easy to do this. So once you set up the folders, that's for later, that's not for now. So you can run. So this is your Google Colab notebook, and how it works. Yeah, how it works is you have small boxes, and then you can just run box by box, and you can add text. So this is a good way to even share code with your colleagues. You also even get an index over here that you can move around your code. And basically this is using Python, and it's not a very strong cloud service, but it's a very weak cloud service, but you can use it for simple model training and model testing. Okay, even deep learning you can do here. You can even go to the runtime, and you can change here to a GPU and TPU. So these are like for people who are doing computer vision. They can even experiment the models over here. So I advise you to, especially when you are collaborating with somebody, this is a good place. Okay, so all we have to do is install the scikit-learn. It's going to give you a warning, and then you run it. So this one will not do the optimization part, save time. We'll just do the first version running the model. Okay, so it's going to download. This does not use your internet, so don't worry. Then I'm downloading the famous data set called Irish. So this is the one that you use also in R when you are learning about linear models. It's the same data set. And you can see it as a matrix of data that's called an NumPy array, or you can see it as a table, which is much closer to what you do in R. So you have the length of the set of, that's a leaf part, right? Flower part, the length of the width. Cool. And then you can do some plotting with it to see how it looks like. You can see the different classes, right? You'd expect this class to separate very well, the red class, and the same thing with the pandas. So this is just for you to just see different tools. So the NumPy in Python is very common that different packages do the same thing, and this is a case of that. Okay, they also both use matplotlib. Then it's going to do a small decomposition. This is a tutorial that is online, so it's not like I invented this. So they require this decomposition. This is some data engineering, right? And you can even see it in 3-dimension, the PCAs. Very beautiful. So the machine learning part, if you go to the web page of supervised learning in scikit-learn. So this is one of the most standard libraries of machine learning, but basically useful, I think, for the table data, structured data. It's called structured data or unstructured data, but not computer vision stuff. This is not the library for that. And you have dozens of algorithms. Okay, you can enjoy yourself. There's a lot of stuff here to see. Neural networks, blah, blah, blah. The neural networks are a bit weak in this package, but they are fine for playing around. And we are going to do a random forest classification. support vector classification. Also in Python, they separate this, not the same name. And an MLP classifier is a neural network. So it's another name for neural networks called multi-layer perceptron. And MLP, that's what it means. Right. And then you just train the model. You have, in this case, we have, if you noticed, we had 150 samples. So it's not that much for example, a neural network or a big model, but we'll try it. So we divided it by 80 fraction of 80%. So 80% goes for training, 20 goes for prediction. So in Python brings all these functions. The cool thing in Python sometimes is we have all these functions made for dealing with data. So it's easier. What happens is in Python, once you have an object, you put a dot, and then you have all the functions available of that object. So that's another. I don't know how many people work in R, if this is work in Python in MATLAB, but I'm trying to give this insight. Yeah, so then they are trained over here. They are created the objects, and you see, sorry, not trained. You see the object is created as a multi-layer perceptron classifier. And we can see the parameters of the model. So for example, this is the random forest. It's going to use bootstrapping, is not criterion for purity is G. You can have other ones, how many lobes you get, none, that means it's going to use as much as possible. How many samples for each split. So those are the parameters that we were talking before, okay? And each model has their own parameter. So if I, for example, check the SVC parameter, it's going to have another set of parameters, right? So these are all things that you have to experiment before.
Or when you split the training data, there's like data called samples.
Yeah, there's a function from pandas. So then you have all these different parameters inside. This is the kernel that's going to use for the model front. So then we can just run. And you can see here, you can set your own parameters. There's two ways of doing it. You can do it explicitly, like an estimator equals to something, or you can do with this double asterisk, which is a special Python instruction. And you get the same. And then you can see that now your estimates are 500, while before they were 100. Bootstrapping is a way of resampling the data so that it avoids avoids correlation, minimizes vector correlation. Bootstrapping is kind of a way that the random forest has to avoid overfitting, let's say. And then this is the training moment. So this is actual training. This is how much time it took for you. Just have the train data, the target data, and let's train, and it's fit. So your models are done. Now you can see how good they were. They were really bad. So they were actually 0.26% accuracy for random forest, 63% for support vector machine. And then you say, okay, now I'm going to try different parameters to see if I improve my model. And you might, remote sensing, this is done by hand often. So people just try around different parameters, right? And then you change and you see there's, your support vector became worse, the artificial network became better. So, and it improved by 20%, double the accuracy. So parameters can make a huge difference in your model.
What kind of change you implemented to optimize?
No change, no method. I just select another parameters and
Okay.
so the next script would be one that you actually optimize. So if you go, I'm going to skip so that we go to the fun stuff. My output variable is the class. So there's classes of in the Yiddish data set, these classes of, yeah, I could have shown that it's the classes of plants, I think species names. But I could have shown that, I forgot. But if you go to other script, now I'm not going to run it. It's not slow, fast. It's not very, how do you say, takes much time, but you can use RTM inversion is what we want. So we go there. So, but if you go to this random forest optimization, you can even go there and change to your own neural network. So in this case, it would actually do two types of optimizations. One is called Bayesian grid optimization. So it does a grid, but it does not test all the points on the grid. It uses Bayesian optimization to find which points of the grid it should test. And then the other one is has three structure parts and estimator. It's kind of a Bayesian approach. Okay, that is built to one package called HyperOpt. It's a famous method in machine learning. And if you do this, you set up the space that you are going to try, and then your algorithm is going to run and say, this is improved, the loss, and in the end, hopefully your model is better. Not always, because it might take time, especially in Bayesian models.
What about increasing the space and reducing the space?
It has a big impact. That can have a huge impact, especially in Bayesian models, because you have to see, so Bayesian model will start, if there's few evidence in the beginning, it will need a lot of time to get to the right model. So if you have a big hyperparameter space, you need a lot of evidence. So of course, and especially if you have a lot of parameters, you need even more evidence. So it becomes Bayesian optimization is usually more on the end. Okay, does this make sense? I was too quick, I think, but at least the collab works. Okay, right. Any question?
You will not show the optimization.
I think we could save that time because it's already 12:30, 12:20, right? So, I mean, I can show. Okay, let's do it. Let's do it. Let's do it. Yeah. So one thing you should do is when you should close the previous runtime, because then you might get kicked from Google. So in Google Earth and Google Colab, if you are running stuff and taking too much, they might just block you for 20 minutes so that you stop abusing. That happened with me when I was doing an interview. Computer vision, and then I was trying always in the GPU, and they just out. Okay, goodbye. Yeah, I didn't get the position. I guess that's why. No. So this is the same thing. You have to install some packages, scan various. I'm forcing you to use a specific scikit-learn because I want to have a specific function. And the same thing. So in this case, the data is breast cancer. Predicting a breast cancer, so much more features, predicting breast cancer occurrence. We're not going to see which data is what, but let's say it's a table of a bunch of information about breasts. And then you separate the same thing as you did before, right? Train and test data. And then here, you basically set the number of times you are going to make a trial, the number of cross-validation. This is input data for the optimization. So it's going to do internal cross-validation. And random state is always something that you should set if you want to make your models repeatable. Because otherwise you run into one day you have accuracy and another day you have another accuracy. So basically you set your model to you set your computer to start from a specific random point. Because computers don't have random data, right? It's a pseudo-random table that they use. That might be another concept. Right, so you set up your model, okay. First error, okay, I forgot to run this line. It's fine. And then if the model is set, yes, it's going to do Bayesian grid search. So basically, I have a set of parameters. Let's say I set up my samples of leaf is going to be a real number between 0.001 to 0.5. My minimum samples on the split is going to 0.01 to 0.5 from a uniform distribution. And then you have number of estimators, that's the number of trees in the forest, 50 to 100 by a uniform distribution. So it's like everything is random here. Okay, the grid is kind of random or uniformly distributed, let's say. So then you can just run.
So this would be kind of private.
Yeah, so these are, you're just giving the space. You're telling your model, try this space and change these parameters in this space. And then your model is going to try. And it's going to convert, use Bayesian inference to do that. You don't see any plot, it just runs. It's in the background, but it's doing it. And sometimes it takes a bit of time. So I can actually probably just tell it to run everything. Run after. So this way, as we start, it is running. Yeah, just wait small minutes.
So here it's already the optimization.
It's already running.
So the model is trying all the parameters.
Yes.
And trying to decide which is
Yes.
the best.
And then in the end, he's going to tell you. So if I go to this, oh, I cannot because I just ran everything. Now if you go to this object, there's a thing that says the best parameters. We'll see it a bit later. Okay. So this is the other 3,000 estimator. So it's the other method. And in this case, you set up the space. This is the same space as before. It works a bit different the way you set it up. And then you have an objective function. So basically, it's the same thing that we were talking. We have to define the error metric. So it's kind of, that's what it's doing here. It's defining the error loss metric. And then it returns a dictionary. This is a technical stuff. It returns a dictionary. It has to be written this way for the model to run. And then you can see, for example, test a function. You can see what happens when you change different parts. And now it's doing here on the bottom, it's running the model. So for example, here you can see what happens to your error when you change different parameters. Okay. Now it's optimizing. Here it was optimizing to doing this reading. But yes, yes.
Already optimized.
Yes.
One.
Yes. So two different methods. And they find, as you can see, they find very different results. So this one is like 0. And then 936 and this one is totally different, right? So here in this case, the way it runs, you have to come here.
Where do we look at which one is better?
We'll see it later. So then we have to put this model here. Oh, and as you can see, because I set the random state, everything is equal. But if I had not set, this could be a totally different number than I tried before. And then here you try the model, and they are the default model. So this is the default without any optimization, 0.55 accuracy, and it equals to 0.57. So you probably would have to do this a lot longer to get better accuracy. But if I do that, then it takes the whole day. So they improved, and they actually found in totally different model structure, they found similar accuracies, which is also important because often models can get the same results with totally different configurations, right? It's a bit data problem. Make sense? Maybe here could have some plot animations. If you go to the YouTube and stuff like that, there's a lot of descriptions about optimization algorithms and swarm and Bayesian optimization. So it's much better to get that information clearly described there.
Do you know any platform for learning all this machine learning and getting a certificate?
Oh, I don't know. I think those Kaggle web courses, and there's a lot of Neo colleges and stuff like that. Yeah.
One lesson for 3 weeks and another.
I can write a paper. I can sign the letter that you were paying attention and asking questions. So I will close here.
They use machine learning, they use also something like gradient descent, like deep learning.
Yes.
I could see we got different results.
Yes. So they use so gradient descent or stochastic gradient descent is one of the common algorithms for measuring error. Basically, you just so that people don't know, you calculate the model with parameters with slight changes around your point. So you are here and you see what happens if I was here, what happens if I was there. It's okay, this one is better, so I move this way. And all of them kind of use it. Okay. But of course, then you have like swarm algorithms and stuff like that. Bayesian optimization might not use stochastic gradient descent. It's going to use, it might use actually, I don't know. Front. Okay, so congratulations for the people who click the buttons. You have your first machine Python algorithm and also optimized, I think, right? For the other ones, you can try it for your presentation maybe. Yeah, we will do it. So this is the preparation explaining what you need to do, right? It's also on your presentation, so you can actually follow. So by the end, you need to have these two folders, right? Which we didn't use now, by the way. So auto machine learning. So the auto machine learning, we were talking about, you get your data, and we talk about this in other parts. You have to explore your data. Somebody was saying, please look at the plots. And then you have, please see what missing data that you have. Now calculate the index. That is okay. And now you select the algorithm you're going to use. And now you train your algorithm, and you find that it's wrong, and you go back to get more data. So you are stuck in this loop. This is where kind of we all are, kind of some in general, right? And you go back and forth between these parts. And the AutoML workflow tries to substitute you. Okay, so it's kind of automating the engineer, let's say like that. And that's the main point of automatic machine learning. Of course, this doesn't necessarily mean that there's no expert anymore, but there's a bit less of an expert. Yes, yes. At least if you go to work in a remote sensing company, yes. Of course, the machine is not intelligent, right?
Because Nuno, it seems like too good to be true.
Of course, it's too good to be true. And these models are made in general, and it often, it often depends on the application, how it works. But you have to understand, for example, big companies like Amazon is trying to provide a machine learning algorithm, and they have a cloud service. They cannot have experts for the thousands of cases they have, or hundreds of thousands, right? So they have to have some machine learning, some automatic. So this, for example, AutoGlue only from Amazon. You can also use it. Okay, so automation is to try to remove the entry level, so you don't have to know so much about statistics, to try to deploy the services, and to minimize the time that you have an expert looking at the data. Basically, that's the point, right? And in general, they have three components. You have your input data that your model should be able to understand what you want to do with it. You have an optimization metric, how much you're going to measure your error, and you have the time. You tell, instead of telling your model number of iterations, you tell them I want the model in the next 10 minutes or 5 minutes or 30 seconds. So that's the difference, okay? And then you have some 10, 20 frameworks, and they usually depend on the original language of the machine learning. For example, AutoWeka is used on Weka. Weka is a machine learning language. Sklearn is for Sklearn is the one I'm going to use. Teapot is for Teapot. Teapot's not for Teapot. Teapot is for something else. H2O actually you can use in R. So if you are an R user, H2O might be useful for you. GCP tells the Google is from Google. AutoGlue is from Amazon. And AutoGlue is very interesting because they don't know heavy computation. Let's say they kind of minimize the computation. It's actually quite an interesting approach. But I'm not going to dwell on it. You can ask me about it. We're going to work in Autoscaler, okay, which is the scikit-learn. It's the one that we can use in Nmap, for example. It's also very easy to use for remote sensing because it's about table data. Okay, what is a scikit-learn? It uses scikit-learn. It's one of the standard Pythons. It's made in some French group. It has a cache approach to solve the problem. This means cache means combined algorithm selection, never read optimization, or it means the money you save by getting rid of the expert. I don't know which one. And then you have basically the main strategy that they use is concept of meta learning, which I'll explain, and a Bayesian optimization. It's developed in German by a German group in Freiburg, and the meta learning is made by what it is. They pre-train their model in public data sets. They pretend, for hours, months in different data sets, and they have this library of pipeline of models. Okay, and every time a new data set comes in, the first thing they do, optionally, of course, you can remove this, is they see if your model your request is similar to anything they have in the library. And if so, then they start with the parameters from that pipeline. So this makes the optimization faster, okay, and more consistent in the results. So this is actually very interesting because you could think of this for remote sensing and active learning, right? You could have a meta learning approach for example, RTM inversion. Pick up from previous experiments, and that is in your library. New data comes in. Is it similar to the meta learning? Then it goes. So this is kind of the general concept of meta learning. And then once your data comes in, this is your data set. It's nice implementation, and then it compares first your information, and then starts the Bayesian optimization part. And then it's going to do the first, see what data processing steps are necessary. Do I need to, for example, get different balance, check the balance of the classes? Do I need to do one hot coding? That's one strategy. Then it's going to start running PCAs and stuff like that to see if that improves your accuracy model. And then it's going to try different algorithms. And it does optimization of all these three components at the same time. Okay, using the Bayesian inference, which that doesn't move. So maybe I have to click. It moves very slow. So it's like the algorithm is a bit slow. So, but basically, the Bayesian optimization is increasing more samples, and as he gets more samples, he knows better how the function behaves. And hopefully, you find the best fit in the function.
Did they impose the data structure, the input and the shape?
Sorry?
Did they impose this structure and the shape for the input data set?
What do you mean by imposing?
Okay. Because the model, some of the time they require certain input, the structure.
Yeah, so the idea of the model, for example, if you're missing data, this is that preprocessing will apply some models to try to solve the missing data. So that the point is that you don't do, of course, it doesn't mean it solves all the problems, but it will try to solve all the problems, let's say. Okay, so the idea is you don't have to do much, right? Okay, other than give him a data and a target. So then that's the point. The point is to pick up the remote sensing expert and throw him out. Okay. It works, right? And the idea here is obviously to reduce the human in the loop and of more automated approaches. I'm going to show this. Actually, this is from a previous presentation. So basically, we can see what happens with the model, what it's trying, and it should be prepared for your tasks. And this is very easily deployable. And of course, the main goal overall is that you are able to get state-of-art results. Doesn't mean it's the best result in the market. Usually in competitions, what happens is AutoML is on the top, and then after a few weeks, you see AutoML is no longer in the top. So humans got better results. Maybe looking at the AutoML outputs. So that's the point. Okay.
It's two in this animation.
This is Arnold Schwarzenegger, the governor of California, and the other guy is I think he was in Metallica. Kirk Hammett. I don't know. Pronto. So, any questions?
What about the computational resources?
Heavy. They can be heavy, especially. I mean, it's less with the Bayesian optimization. It's always a bit less in a way because it kind of tries, less number of points to get a good accuracy. So in theory, it might be less, but it also depends on specific tasks, right? But it's obviously every time you are computing different combinations, especially when you do feature selection, it's a very heavy computation.
But where the computation is done, so
In the computer.
That you are, it's not on the cloud.
In this case, in the cloud, but in the Google Colab training cloud.
So it's not kind of your problem, right?
But you pay for it. If you are doing it in a web service, for example, from an Amazon, you are paying for it. So of course you might not want to do it.
Okay, but if you are doing for a research project,
The Brussels pay for it.
because you have to.
No, if you are doing computation, the computer is doing computation, right? So either your computer is doing the computation or the cloud is doing the computation, but both ways you are paying for the computation, right? But yeah, so it might need a lot of computation, especially, if you, for example, create a meta learning library like they took months, right? Because they have to compute, make sure that they have the best pipeline, let's say for the task X, and then they have to do the same, and they might have to do cross-validation of your data. So it becomes a lot more complex, but of course that's for research. For application, it's a lot less. And especially if you can tell him, give me a model in 30 seconds or 1 minute, that's a lot less computation than you by hand. Yes, you'll hopefully see that, but the time is getting short. It's already 1 o'clock almost, right? So maybe what I do now is I just go all the way down instead of going to the collab, because we're going to do the auto scaling and all that, and then go directly for the RTM inversion, okay? So let's skip this part. So in the next script, you will have a section that will be about auto scaling implementation. You just try it out. So this is the discussion. We don't have enough data for biophysical traits, blah, blah, blah. And the data sources, then the alternative is to use some simulation of the traits, right? I'm kind of skipping through this because this is an old story for you by the first day. And our problem that we're trying to solve is to go from spectral data to biophysical traits. And our algorithm will try to find chlorophyll content and leaf area index from Sentinel-2 data. And this is our outputs, and this is also going to be our features. That's why it's in blue, okay? This is not new, I think, by now, right? It's boring, actually. And then we are going to use in a pixel-based classification. So there's like, let's say, 3 ways at this moment: pixel, object that is kind of dying off, and convolutional neural networks, okay? Which is not what we are doing now, but there are AutoML methods for convolutional. For example, AutoGluon can work with convolutional neural stuff. Now our exercise is we're going to pick up process data, generate synthetic Sentinel-2 data, put that into an AutoML pipeline, and then pick up our data from Google Earth Engine that you guys will not do also for the time. Do predictions in LAI, and then I'm going to compare it against data from NEON, the National Ecological Laboratory. And I've been processing digital hemispherical photography, so that's photography that you take up to extract the LAI. And I have an algorithm to calculate that. And then we're going to see if our model fits to the real data and fits to the synthetic data. And tomorrow was today. The study area is the National Ecological Laboratory. Maybe you have heard about it. A bunch of sites in America where they collect all data, UAV data, hyperspectral data, LiDAR data, everything is there. Biodiversity data, so it's actually good study places. We're going to work in this location, and our data is from there, and I process based on the same description they have in this package. Okay, so completely free. You don't even have to register, which is very nice, right? Because it's not like the Europeans do it. We don't do it this way. We have to register 5 times. So this is the place, okay? And our validation points are these 3 locations. I don't even know if they're a forest, but front. Okay, let's go for it. I have to go to my video. Yeah, so they have a cameras taking pictures, and they go there every month, and they also do some around the park. But these are the ones that are yeah. They take pictures up and take pictures down, and then you have to extract how much light goes through the canopy from the top and how much leaf area you have on the floor. It's an older technique, but it's very time consuming because the images are big. Leaf. Okay, so here we go directly, so we skip the process because I will also have a function that will explain about how I do the process processing. I will explain that directly on the RTM inversion. And you open this in a new tab. Okay, so one thing I would have explained is autoscaling is a bit harder to configure in Google Colab. It's a bit annoying. You have to update function changes a bunch of packages, and this is the problem of working online. Of course, if you're on your own computer or your own server, you not have to do all these updates all the time. But what happens online is package X gets updated today and package Y tomorrow, and then suddenly your library is giving you warning. And that's the issue here. Okay, so we have to install the whole autoscaler first. This takes a bit. Seconds.
There's no possibility for environment.
Probably.
So the data directly consuming from the RTM.
Sorry?
The data collecting for the processing is directly getting from the RTM.
RTM?
Google RTM.
Yes. So no. So you have the images from Google Engine and you have the process from the other side. So this is like the hybrid inversion. Okay, you are picking up synthetic data, generating synthetic data, okay. Yeah, this is very boring, and you have to repeat this in every script with the process part. But there's no alternative. But otherwise, my script would be, very long, and you get lost on it. So this way, you can run one by one. No, it will predict multi-output. It's going to predict chlorophyll and LAI, but I only picked up validation from LAI. Because that actually took me a week to process 1 year of data for that place for 3 points. Very frustrating, right? I feel like, God. Okay. Yeah, so it installed everything. And one thing you need to do in Google Colab, again, if you are working in your server, in your computer, you don't need to do any of this. But in case of Google Colab, you have to do this because it resets variables. For the people working in Python, this makes sense. So if you run autoscaler, for example, I'm running autoscaler here for that cancer data before, and I'm giving in 30 seconds only for training. Okay. And it's going to run for 30 seconds, and then you'll be able to see what is the output of the autoscaler. 30 seconds and 9. Okay, so this would be, so for the cancer data, this will be the output of my pipeline testing. So it tested 9 models, and this is the accuracy of each model, and this is the type of processing that it did for each model. Okay, and then you can sort this, where it makes more sense. So type. So these are data preprocessing. These are feature preprocessing, and these are the algorithms preprocessing. There's also another feature preprocessing here in the end. So then you could even, press, for example, first model that is here, and you can see the steps that it did. Got the input data, categorical transformation, information, linear, blah, 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 processor, gradient boosting, and then output, okay? And then if you pick up, press one of the buttons, you can see the parameters here on the bottom. And if you press, for example, let's say gradient boosting here, you can see the parameters of the model over here as well, okay? Yeah, and the final prediction, then the final prediction of your model is based on this ensemble. So the output from here multiplied by 3.20, output from there, okay? So you can use this even to search for models. Instead of using it for applying, you can try to use this to search for pipelines for models. Here, ensemble weight, sorry, it's very small. Ensemble weight. So the final prediction of the model is not based on one single output, but it's based on the weighted average between the different models. So each of these ones is a model. Each line is a model or a pipeline, and this is the weighted pipeline. So this is a good way to test models, right? You can use this to test different models, and then if I know this algorithm is usually better, then I'm going to focus on using that algorithm. Right, and then of course you can see for the different stuff. Okay.
Can we modify the models?
Yes, we'll do that. Then this is to connect to your Google Drive. Okay, so it will
For the data.
for the data. So it will prompt you, please connect, and then you choose the drive, and hopefully everything went fine. You have to get this code, and then you just go here and okay. And now it will be connected to your Google Drive when it's finished. And you can see your drive now here. It's on the side, my drive. All my crappy stuff I have there is there. Then ProSale, I would explain, you need to install a package, blah, blah, blah. This will be before. There's a ProSale Python. Yes, there are like 3 or 4 packages of Python ProSale. But this is the one from UCL, I think. So they are the ones that are usually more updated. I don't know if they even have the new stuff. There's a ProSale, and then which is from Watson or something like this. And then, yeah, I think so. Yeah. So there should be, or at least they will have a wrapper for using Fortran or whatever, a wrapper to call the Fortran package. Then you import and everything is fine. Then I have a specific function to control what is inputting on ProSale to simplify my life. And this is what it's doing. And then there's a function that it gets the response curves from the Sentinel data and converts the hyperspectral to Sentinel data. So this is what it's doing here. And then it has another function that is going to generate spectral data based on the table. Okay. So, I mean, this will have to run in another package. We can try another day if you want to try. So believe it works. So what happens is you give it a table of traits, generates traits and angles, generates spectra, and then from there it converts to Sentinel data. Okay. Actually I have a test over here, maybe, to see if it works. Yeah. So it generates. So these are the 13 bands of Sentinel. Okay. Nice. I didn't know I had this. The 9 bands of Sentinel. Sorry, the same. Yeah. Yeah. From ProSale.
Only for the Sentinel 2 band.
Yes. Yeah, for ProSale. The 9 bands. I removed the 8 band. So
what is the spatial extent represented?
There's no spatial extent. This is spectral. Yeah, it's just a spectral curve. So this will be band 2 because now I'm selecting bands. So this will be band 2, band 3, band 4, band 5, band 6, and 7, 8A, 10, 11.
Of the
11, 12.
all the models.
Of the ProSale. So this is just a plot of what's happening in ProSale. It generates hyperspectral data and then generates Sentinel data. The same thing you see in RTM.
Yeah, but why are there so many?
There's not so many bands. It's a line. It's 9 bands. Here. It gets band 1, 2. So this, you have to see these numbers are indexes. They are not band numbers. They are 9 bands. So I think, right? 4, 8, 9. Because I know where they are. So it creates a matrix of 13 bands, and I select the ones that I want.
So you already know what you want.
Yes, I would have shown this in the ProSale part, but this is basically you can select I made a function that you can select if you want the first band, like band 1, band 2, band 3. That's what I'm selecting that dictionary.
Why not all?
Because they are repeated, like band 8 and band 8A. They're kind of the same except for the wavelength. Yeah, you could put them, but it doesn't matter. Just put 9.
What if we don't know that? I mean,
But you have to know if you don't know how to convert the hyperspectral to sentinel data, then you cannot do it, right? But there's functions that you can use to do that. That's just that. Understand? So if you need to make a function that converts from hyperspectral process data to sentinel data. Okay, your process outputs something like this in the presentation. So this is the output of process. Wait, sorry, this one is an hyperspectral curve, which each point is one band. Okay, and this is the wavelength. Okay, so this is not what sentinel measures. So but there's a function that converts this data, the sentinel data, provided by AZ, like a table. And you can use that table to convert. Okay, for each sentinel, that's to do the response.
I mean, first you run the hyperspectral data with the process model, and they will.
Yes, you have to do that. Yes.
Take the spectrum from there and
Yes.
implement on the sentinel.
Yes. You have to do that, otherwise you don't have sentinel data. Okay.
There's no preprocess.
Maybe I need something that web. In the web you do this, in the web there's a 702 data. You don't have that, and no.
I'm going to do prediction in sentinel data. So my model is going to be trying to work with sentinel-2 data.
He try to generate a sentinel-2 replicate data, and then he will validate with the original data. He's trying to.
So I'm trying to train a model. I'm trying to train a model that picks up sentinel-2 data and outputs leaf area index. The input is sentinel-2 data, so I have to use sentinel-2 data. Okay. So I have to generate sentinel-2 data to train my model.
Can you write in the board?
But I don't have a
Yeah,
pen.
there is.
What do you want me to
On
write?
the board. On the board.
Oh, okay, there was another over there. Okay, so what do you want me to explain? That? Okay, so think about, okay, the process is actually already explained here in the, here. You pick up your process radiative transfer model, you generate hyperspectral data, and then this hyperspectral is converted to sentinel data. What do you mean you don't have that? You have that. I made a function that makes that.
You cannot compare that.
What?
I just curious, you cannot get the sentinel data
From what? I don't understand. Because you cannot get sentinel data from where?
I mean, you can also get sentinel data from Google Earth.
Yes. And how will you do that? Yes.
You don't use it as input. No.
Because okay, you have sentinel-2 data. You have this, okay, imagine that like this. You have taken a picture.
Okay,
Yeah, you have a picture.
You can explain what is
You have a picture, and this band, you have a value of like you have a, I don't know, you have a value of 1. How much LEI is there? It's the issue, right? You're setting out 2 image. I don't know how much LEI I have in one place, right?
No.
So how do I make a model? We send out 2 data to go to the LEI.
Yeah, but she didn't
His
understand
base
what
data
is
is the hyperspectral.
Ah, okay.
That's why.
I thought she had process. Ah, okay.
She didn't understand
His
that.
base data, how he started.
I'll explain here
is
then.
the hyperspectral data. And he used the process model on the hyperspectral data to generate the line. And now he compared the line from the sentinel.
She doesn't know what is process.
I'll explain the process. Okay, that's easy. That's easy. I skip that present part. That's fine. Okay, so this is known, right? You know how light transfers in the atmosphere. You know how light transfers in the air. More or less, you have an idea, right? So process is a model that simulates this. If X light comes to the atmosphere, it interacts to the atmosphere that comes to the reef. This is going to react this way with the type of canopy, blah, blah, blah. Okay, it's like a physical model. And once you run the different parameters of that model, your output is an hyperspectral profile. Okay? It's a profile like this. So I pick up, I say my leaf is M, my chlorophyll content is blah, blah, blah. You can hear my chlorophyll content? And get equivalent water thickness, and then I run it and I get an hyperspectral profile.
Okay.
Okay,
Yeah.
this is easy. This is not an issue, right?
No.
But my satellite data measures this, right? And I want to measure from here and predict vegetation traits. Okay, so that's what I'm doing. That's what Procel does. It does this part, but I want to go from this part to this side. That's called the inversion.
Yeah.
Okay.
I remember that.
Now I see.
Okay, right, later. Okay, let's move forward because this took us over. So then I add noise to my data set. Okay. I add noise to my data set. This is something that is usually necessary. Even in machine learning, you try to degrade your data signal a little bit to make your model not overfit. So this is a common to the spectrum. In spectral base. So it's based on a paper that we do it.
Why are you adding noise?
Because your model will overfit otherwise.
Okay.
Okay, and this is common in every machine learning. They do data augmentation technique and stuff like that. Okay, and then we generate data, 1,000 samples. I'm going to generate 1,000 samples based on a specific sampling design, and then by the end, I'm going to have a plot. I think do a plot, and then I can also describe the data they have inside. Okay. We didn't plot, that's fine. So you could go to Autoscaler to get more information about it. I'm going to skip that. This is just preparation of your data set. So I have a train target is the Y and the train X is the data. Yeah, and then I'm going to try my AutoML model for 30 seconds. And it's going to give me a warning that it does not have any multi-output model in the meta-learning library, which is kind of expected. They didn't train for that. Multi-output sometimes are not as common in machine learning. They are becoming more common. And then after 30 seconds, I will have a model, which I think doesn't even use Gaussian process in this case. It's going to be accurate without using Gaussian process. So it's already what? So it's already mean absolute error of 1.8 in MAA, 0.36 in LAI. And then you have the pipeline over here. It's very small. It doesn't have much time to test anything. Yeah, and then you get the model. Okay, no Gaussian processes. You see extra trees, nearest neighbors. And this is your plots one against the other. And it's already correlating in a nice line. This one was supposed to train for 5 minutes, but that's too much. So I'm going to just train it for 102 minutes or a minute. Okay, that's very small. Let's do it. Yes. So I'm going to put 120 minutes. So that's 2 minutes. And it's the same thing. Okay.
You don't have much on the GitHub, right? You do not put in, you don't have much on the GitHub.
What do you mean? You don't have much on?
Like, do you have many scripts?
Yeah, I put a lot of stuff there, but don't expect it's organized.
No.
It's a mess. So you're supposed to be 300 seconds, so it'll be 5 minutes. You have to wait 2 minutes now. Did you understand the process meanwhile we're waiting? Did you understand what I'm doing? Okay. What was the confusion there? Okay.
They have the video and.
Okay. Okay.
It's really complicated.
Okay.
But for validation, like, you know, in Snap, like inbuilt default live processor is also using the process model better.
And? But what can you do about the Snap neural network that you use for biophysical trait retrieval?
And what method do you use for?
Yeah, but can you do anything for biophysical trait retrieval in the Snap toolbox? Can you change anything? So then, yeah, that's the problem, right? So you assume that their model made very 2006 before, you know, scaling computation is great. It's not. So that's the thing. Those tools are nice for off the box use, but if you want to do better, so it's getting very late, I think. So I will not do much more, I think, after this.
Yeah, because lunchtime.
It's lunchtime, I think.
But I guess you can guide later on people that are interested
Yeah.
in the next coming days. And there are some groups maybe that want to make use of these techniques
exactly.
that you supervise.
Exactly. So you could see like the model will improve a little bit in comparison to the previous thing. And you get now a lot more testing of models. And now Gaussian processes start appearing in your model, for example, Gaussian processes. And they are the top 3. If you run more time, they're like the top 10. They take over completely. And this is kind of Gaussian processes are the best model. And you can see the different parameters. It does not change the kernel, but it's possible to change that.
The Nuno Gaussian processes is one of the top performing.
In this case, it's always the top performance. So, and it finds also like sometimes you might have to do pre-processing Gaussian processes. You have to kind of see. I don't think it did in any of these cases. If you train it for longer, it will start doing pre-processing of the data as well.
And does it include also the deep learning or
No, this is for sklearn.
Okay.
So sklearn doesn't really have deep learning, but there's other models called AutoKeras, which is for neural networks. H2O, I think also is, but I don't think the problem is Gaussian processes are not so much implemented in many places. So they're implementing the Bayesian part, which you don't touch.
And how much is it better? And it's, let's say, more accurate results in your opinion compared to.
So the Gaussian processes have 2 benefits. The Gaussian processes have 2 benefits. They are relatively easy to understand and apply. They have good accuracy. They have very good accuracy in this specific case, and they have uncertainty. Okay, so these are the 3 things. The main issue is they don't scale. So once you so the Gaussian process has to store a copy of your input data and a correlation matrix. So every time you add a new point, it becomes super heavy. So that's you have to see, like if you have maybe 4 by 4, then it goes 5 by 5, it exponentially grows in size. That's the issue in Gaussian process.
So that's the reason why it cannot be trained with lots of data. Exactly. It's out of control. So it's very powerful when you have small data, but when you start doing experiments with big data, the Gaussian processes will not be performing just because of these reasons.
And then the other great benefit of Gaussian processes is that you have all these ways of working with the kernels to make your assumptions imposed into the data. So for example, let's say you are doing carbon monitoring and you know that it's going to increase the amplitude of the changes in carbon. So this is something you can put in your prior. And by imposing that, you impose a very educated guess. Okay, I can show you a drawing how that happens in the model, but that's a good part of that process. Right, so that's it. So now, for example, if you wanted to, now just the last part, because I'm finished and then we go. You could see also the accuracy over time of your model. And this is what will happen. So your model, as you started running, this is also that example at 10. This is ours are wrong. Probably American or something like that. From 2 minutes to at a time, what was happening with the accuracy, and of course, you hope that it fits over here. The problem is sometimes you have in Gaussian processes that they overfit. So there's this change. This complicated is a re-implementation of a new class. So this is good for the people doing Gaussian process. You can re-implement the Gaussian process class, and you could have a parameter here to change the kernel, for example, and have optimization on that. So this could be really easily adapted for our cases. Then you put this in your model and you test it. Now I'm going to train it only for 30 seconds. And hopefully, no, 30 seconds is too small because I know I'm forcing the Gaussian process, that's fine. So now I'm forcing the model to use only my Gaussian process object, the normal one and the random forest. And those are the only models that are going to be tested. And then you can save it to your computer and you'll be able to load it. Okay. So if you want to run the rest, you can one day try to run it and send me an email. Yeah. So here, for example, you would see primitives. The R square of the first Gaussian processes. So this is random forest was the best one. This case, so this, for example, already did pre-processing, and then the Gaussian process 2, that's the one I just defined. Yeah, and the next one is going to be the normal Gaussian process in the same pipeline. But it's done. And this will be, if you train more time, you get better prediction. Okay. But and in the end, it saves your Google Drive. So now, for example, if you wanted to load your model, it would be here. Okay, it's saved into your Google Drive. Okay. And what will happen now is we will pick up these models and apply them to remote sensing data. And then we will see, but that is for another adventure. Okay. I think it's too late for that.
So it's same like, I mean, we use the whole model to separate data and just predict the, right?
Yes. Any questions? Because I don't think we have time to train the model, but by the end you will have something. I probably have it somewhere.
Can you just show the code that you use for this training and testing? I just want to see which parameters you consider for train and test.
Where?
In Plovdiv.
Which parameters regarding what?
No, when you put for training and testing, it's the parameters like zenith angle or.
Okay, the pro-sale parameters. Yeah, I didn't show that because I skipped. So there's this function is a function I made kind of custom to generate parameters. So they kind of vary from 15 minimum angle to plus 45, 3 plus 2. This has to do with this has to do with the original data. I went there to see what the variation. I would have shown that for time. And this is the carbon light, so it can go from 60 to 80, and the LAI can go from I think 6. No, it goes more than that. Sorry, from one to 7. Sorry. And then I generate the table. Okay. So in the end, you will have something like let me show you my original drive. Maybe that's the best way to go about it. You should have by the end a place like this. You have these predictions here for testing. Then you have tables of your outputs saved in your drive. And you'll also have a bunch of predictions by the raster. And then in the end, sorry, you can download this data. Download. Let's show you folder. And I think we're finished after that. Yeah. Oh, this is the chlorophyll. So to download the other one. So now you have a LAI map for that location. Great. Yes, this is a prediction. Great. And if there is questions, I can answer. Otherwise, set up this very quick. This is like a day, maybe. But the processing, took time is processing the digital hemispherical photography, which is much more complicated.
But Nuno, can we apply this now with our own data, maybe on the project tomorrow, so that you can?
Yeah, I can.
Because what do you need? The training data and an image. That's how.
Yeah, I just need a pro-sale and an image to predict on, because then you have a model that is saved in a pickle and you just load it in your computer and it runs.
But validation data also?
Validation data, I have some, but I don't have, I just took it from Neon.
Right, but if we have our own validation data.
Yeah, I can, yeah. So this is the way they take the LEI. They take these pictures out and then they extract some angles here. So this took me a week to download and process, and a bit more to design the algorithm.
So,
I think during the preprocessing protocol of satellite units, do you also control the time where you work with batches and patches and?
Yeah, the mini batches and stuff. Yes, you can have those kind of stuff as well, I think, but not on this, not on the autoscaler. So those mini batches are part sometimes of specific models, not of the autoscaler itself. So some of the parameters will use the mini batch and the blah, blah, blah. Yeah. But notice that this is not for convolutions. Okay, this one is not for convolutions. The one that you should use for that type of work is maybe the one from Amazon, at least, because those they have one specific. So they have 3 versions of the algorithm for this type of data: text data and image data. Okay. No, it was almost asking.
I find it really cool and interesting, and it's already now a lot of that dressed, but maybe I don't know. Well, we could continue somehow
Yes.
online or I don't know.
I think in any case, I think the
I was in-
groups, the working groups, you could implement this stuff later on in your project, right? And that's the idea that Nuno will be around.
I lost my composure.
As a teacher, in fact, and that he will.
Yeah, I will help if you want to. This is very, all you need to give to me is to use RTML is a table. For this RTML. Okay? If you have a table with outputs and inputs, that's it.
Right, so an idea would be you could compare ACMO results
Yeah,
compared to
with
what RTML does and see what works.
It's a nice research.
Okay, guys, we go for lunch, but we have announcements to make, maybe a few. You heard us.